Welcome to Under the Microscope, a stage for materials and nanoscience. This podcast is powered by the Science Talk team. Our goal is to provide a stage where scientists can communicate their work and interact with the public. With that in mind, with every episode, we introduce you to a scientist working in the field of materials or nanoscience. In addition to featuring on this podcast, every guest gets the keys to the Real Scientist Nano Twitter account for an entire week. Check it out at realsci_nano. All right, on to today's episode. Enjoy!
Hi there, and welcome to Under the Microscope, your podcast spotlighting materials and nanoscience. My name is Svenja. I'm your host for today. And with me, I have again a guest who is a scientist, and his name is Ketan Madane, and he's a PhD student working at the University of Limerick in Ireland. Welcome. How are you today?
I'm very good. Thank you very much. First of all, thank you very much for having me. I feel privileged and honored to be on your podcast. Thank you very much for giving me this opportunity.
Thank you for joining us and sharing your science and scientific journey with us. We are, I think, very exciting for your research and your research topic. I think it's a bit different, maybe. For me, at least, I think I will learn a lot. So let's maybe start straight away. So could you explain your current research to us in very simple words, please?
So the theme of my work is basically magic processes. Magic essentially stands for modular, agile, intensified, and continuous. So that is a idiom that we have designed, that is magic. So essentially what it means is that you need to, if you create magic processes, it is highly energy efficient. It has less energy footprints. The carbon emissions also goes down. So if the process is modular, it of course has a less footprint. And if it is agile, it is easily adapted to change. And intensified is obviously self-explanatory. And then continuous. Any process that we do in today's industry is batch process. So what you do is that you have a simple stir tank reactor, you have a component A into that, and then you add component B. So that is a batch process. So, but that batch process suffers so many disadvantages. So we need to make this continuous process. So essentially, if there is a process that is there, we we add the magic into it, and we convert magic processes. So that's what we do. And my research is focused on designing and developing fluidic devices to facilitate this magic processes.
Okay.
Yeah.
I just stop you quickly.
Sure.
Right there. Maybe you were going to say it anyway, then sorry for the interruption. Can you just give a very simple explanation of a fluidic device? Because I'm not sure if all the listeners know what it is.
Okay. The simplest fluidic device that we have in any laboratory, or we use it, is a simple pipe.
Okay, that was simple.
That is very simple, right? That is the simplest fluidic device that we work on. And most of the labs in the across the world and all the laboratories, we use a T-junction, right? We have a simple pipe, and then we have a T-junction. A component A is going on in one inlet, and the second component meets at a T-junction. And then that whatever reaction or whatever process is taking place, that will take place at the junction, or maybe down the timeline, downstream of the pipe, and the process completes. So that's a simple fluidic device.
Okay, thank you.
This is a simple fluidic device, or rather, there is another device that I want to show you. That this is a helical coil. It's a simple pipe which is wrapped helically around an axis. What we have done is that we have converted a straight pipe into a helical coil. So now what happens is basically once you change this straight pipe into a helical coil, the entire fluid dynamics inside the device changes. And then you have a better performance in terms of, let's say, mixing or residence time distribution. Now, you get intensified mixing. So the performance of a straight pipe is less. The helical coil performs better in a certain sense. So now these are simple fluidic devices. All the fluidic devices, you can see there are numerous fluidic devices, and there is ample amount of literature available on all the fluidic devices that are being used for different processes. You have static mixers, you have microfluidics. These are also fluidic devices. But my PhD is focused on two devices. One is fluidic oscillator, and second is vortex diode. So fluidic oscillator, as the name suggests, it actually oscillates a jet of a fluid.
Okay,
now, yeah. So the interesting thing is that the fluidic oscillator actually was never invented for the fact to be used for process engineering applications. So the fluidic oscillator is a device that was invented in 1960s, and it was the replacement of then MROIC transistors. So basically, in 1960s, people were actually investing a lot of time and energy to generate fluidic computers.
Okay, so like I guess not water-based, but some kind of liquid instead of a silicon chip?
Yes, correct. So after the invention of PN junction diode and all the semiconductor technology, this field was little bit, I mean, of course, it was replaced by the electronic transistors, because it is very simple to, even if you use a simple pipe to connections of pipe here and there, you can still construct a logic gate out of it. But of course, you know, these devices are bulky, and eventually PN junction replaced it. But this device was there, and this device actually holds a beautiful property. It oscillates the jet of a fluid. And why not we harness this oscillatory mechanism for process engineering application? That is what that was the question that we asked ourselves. Study all these devices for transport phenomena, which essentially means we quantify mixing in them, we quantify residence time distribution in them, we quantify to some extent sometimes heat transfer and mixing. Now, all the processes, chemical processes, or all the process engineering applications involves one important thing, that is mixing. So if we have a device, we quantify these transport phenomena in these devices, and then use these devices for real-time applications, real applications. So as I said, that fluidic oscillator is something, as name suggests, there is a jet of fluid that enters a confined space, and it just starts oscillating by the virtue of geometry.
Okay, so there is no
nothing.
Motor or something, or motor is wrong, right? But you know, there's no part that oscillates the fluid. It's just the design of the device.
Yes. So essentially, the main part of my PhD is I am working in devices without moving parts.
Okay, so you just have a device, and just by shaping it in a very specific way, you influence the fluid dynamics, so it does whatever you want to do.
Yes. So how to, just because of shape, it doesn't happen. Sometimes very interesting fluid dynamics is always at place. Now, Henry Conda is one of the Romanian scientists. He invented a physical phenomena, fluid dynamic phenomena called as Conda effect. That effect is known after his name. So what he did was, I can give you a simple example. Suppose you are actually watering your plants in garden, and you are holding a hose pipe, right? And if you try to bring your finger near the jet of that water jet, that jet tries to stick to your thumb, right? So that effect is called as Conda effect.
Okay.
Right? And how to harness this effect now, right? So how to harness this effect? So what happens essentially in Conda effect is that if there is a jet that is coming, what happens is that jet tries to entrain fluid, surrounding fluid inside it. Because it is going in this direction, it tries to entrain surrounding fluid inside the jet.
Yeah.
If you bring a wall near it, that entrainment is restricted. Hence, the jet, to balance the momentum, it attach itself to the wall.
Okay, yeah.
And that effect is called as Conda effect. And fluidic oscillators works on Conda effect.
Okay. So, interesting. So you built something that's, I guess, is a slightly bit more complicated than watering hose for a garden, but we see some similarities here. Okay.
Yes. The property of fluidic oscillator is that the jet oscillation frequency is directly proportional to the inlet flow rate. So the more flow rate you put inside the oscillator, the oscillation frequency goes up.
Okay.
And
so what frequencies are we talking about? Just a rough number.
Yeah. So we are talking about frequencies from approximately 1 hertz to 20 hertz, depending upon the flow rate. So you can, for the device that I'm working on, has a oscillation frequency roughly from 1 LPM, 1 liter per minute flow rate. It gives 1 hertz frequency.
Okay.
You know, these simulations, so I was coming down. This is fluidic oscillator, one device that I'm working on. And there is a second interesting device that is called as vortex diode. So vortex diode is another fluidic device that has a different phenomena into it. Now, what is a vortex diode? As the name suggests, it has a vortex chamber, and there is, I can show you the device again. So this is the device, it's very small. So it has a tangential inlet and it has an axial outlet. Right. So what happens is that when from the tangential inlet, the flows comes inside, and because of this profile, frill flow gets generated in this chamber. Because it is coming from tangential inlet of this circular section, right? So the flow gets set up, circular flow gets set up inside the vortex chamber. Now, what happens is that once the circular flow, the swirling flow is developed inside the vortex chamber, at the core of the vortex, the pressure drops below vapor pressure.
Okay, yeah.
Now, once the pressure drops below vapor pressure, cavitation takes place. So cavitation essentially is phase transfer phenomena that happens, at a certain pressure. So we use working fluid as water. So water has dissolved air into it. So what happens is if you reduce the pressure, first the degassing of air takes place because water supersaturates. Right? And further reduction of the pressure, what happens is that water tries to vaporize because we are reducing the pressure, vapor pressure.
Yeah.
And it generates bubbles.
Okay, so.
And these bubbles, they are continuously generated and they burst downstream. And because of this bursting, we have shock waves generating over there.
Yeah.
And these shock waves we are harnessing for multiple things for process engineering applications.
Okay, so you basically you generate this vortex or this
swirl flow.
Yeah, swirling flow, and then in the center you generate bubbles basically.
Yes.
Okay, and then your bubbles, they burst.
Yes.
And through these shock waves that are generated by this, you can apply for several things.
Yes, that's how it
Okay.
is.
Yeah.
So these are two devices. So what I do, how do I study these devices? So first I do is that I do use computational fluid dynamics approach to study flow in these devices.
Okay, so you do computer simulations.
Yes,
in a simplified term.
In short, yeah, computer simulations. Now we use one of the most beautiful equations that has ever been, and it's $1 million problem still at Clay Mathematics Institute. So if you solve that equation, you get $1 million.
Okay.
Right. So that's Navier-Stokes equation, and this Navier-Stokes is one of the beautiful equations. So actually, you have a geometry, you apply boundary conditions, and you get the flow inside a device. So before even doing an experiment, we know how the flow is going to take place. So we are actually in a certain sense time traveling in fluidic devices.
Okay. So this is getting a bit interesting here. So we have a magic processes and time traveling. Is this a science podcast?
And yeah, I mean, so you actually predict flow. So essentially, Navier-Stokes has that capacity. In a certain sense, we are seeing future. We are time traveling in devices. We are time traveling in flows basically. So suppose there is a geometry, and if you apply, give some flow rate to this device, what would happen, right? Of course, these Navier-Stokes equation are very simple in terms that the basic law behind is just mass conservation and Newton's second law. But because of this fundamental theory of mass conservation and Newton's second law, we apply it to fluid flow, and we get something called equation beautiful as Navier-Stokes, which does not have an exact solution till date. And it was originated maybe in something in 1800s, and we don't have an exact solution. And if you solve and get an exact solution, you get $1 million. The prize is still open.
This your goal?
So no, that's how the Navier-Stokes. So basically, we solve Navier-Stokes equation to get predict flows in these devices. And then what we do is that as we are simulating flow in these devices, we simulate along with flow. We simulate mixing, we simulate residence time distribution, which is essential for process engineering applications. So we use powerful computer simulations. Then we optimize the geometry so that we get a certain degree of mixing or residence time distribution or what the process, how to satisfy the process requirement. We do these kind of simulations. We optimize the geometry then. So we have a geometry. Now, suppose, for example, there is a geometry which has a mixing intensity of, let's say, 70%. And we want to raise it to 100%. So there should be some geometrical modifications that we need to do. And due to these geometrical modifications, you can increase the mixing intensity. So instead of constructing and manufacturing the device, we do it through computer simulations. And once we have an optimized geometry, we manufacture it and we test whether it is correct or not.
Okay, so in your group, you're both working on the computational side and on the actual
experimental
let's
side.
say experimental side. Okay, quick question. So you already showed a few fluidic devices and you talked about that it's important for a lot of processes. Can you give me like 2 brief examples of processes, like, you know, why should we care about fluidic devices? What are interesting processes? What are, I don't know, important industrial applications?
I'm also working on the application of the devices. So my application is concentrated on crystallization, anti-solvent crystallization. What we do is that we do have model crystallization systems that are already in place. So suppose we have to develop any new reactor, we already have model crystallization system that we use to test these devices. So what I'm working on is anti-solvent crystallization of paracetamol. So
okay, and this is about how to produce paracetamol or how to make paracetamol more, I don't know, efficient in its effects in the body, or like.
So what I am focusing is on particle size distribution of paracetamol. So what happens is that, you know, anti-solvent. So what is anti-solvent crystallization? So we have a saturated solution of paracetamol in, let's say, methanol and water mixture. So the solution is saturated now. Now you add anti-solvent into it. Anti-solvent is, in this case, water. So you have water and methanol mixture. You saturate that solution with paracetamol, and the paracetamol is completely dissolved now. Now you add water as an anti-solvent again.
Yeah.
So water as an anti-solvent, what it does is basically it reduces the solubility of paracetamol inside that solution.
Yeah.
And now paracetamol precipitates out. It crystallizes out, sorry.
Yeah. Okay. So you get paracetamol powder, essentially, right?
So crystals, in this case, crystals. Yeah. So now the crystal size distribution of the forming paracetamol crystals depends upon the intensity of mixing. Right. So in recent study, we were able to show that, you know, we compared our performance of fluidic oscillator with a stir tank reactor. And we had significant reduction in particle size. Because what happens is that the more efficiently your anti-solvent and solvents are mixed, the more mixed it is, the more nuclei will form of paracetamol. And, you know, because it is completely mixed, I mean, we can assume that it is completely mixed. It's definitely not completely mixed because there is a distribution. If it is 100% mixed, it will be just a monodisperse particle size. But, you know, so in what we did was we compared stir tank performance with fluidic oscillator, and we had significant reduction in the particle size, and even spread of the particle size was also reduced. So we use fluidic oscillator for that.
Okay, and this reduction in particle size is good because it results in better
packing
performance, primary packing.
Yeah, packing, and even because, you know, particle size. So packing, yeah, basically, essentially, it is packing of the you know, tablets and all the stuff. So particle size is essentially what pharmaceutical industries are looking for. So we use fluidic oscillator as a good mixing device in anti-solvent crystallization to have better control over particle size distribution. Now, we were able to prove that after a certain flow rate, the mixing intensity of fluidic oscillator reaches a saturation of 100%.
Okay, so you can actually reach 100. You know, in a lot of processes, often you try to reach 100%, but maybe it's not possible.
Yes.
But okay, cool. This sounds all very, very cool and interesting. And I guess there are a lot of super interesting applications. And I hope you will show more of your different devices and simulations once you take over the Twitter account. We actually had a scientist working in microfluidics previously on the podcast, the wonderful Susie Seibt. So if you enjoyed this episode, why don't you head to episodes 187 and 188, scaling down a chemistry lab at the Aussie Science Donut next. And listen to Susie in conversation with my teammate Pranati. Enjoy. I'm interested now. So how did you get there? How did you become a PhD student working with these fluidic devices at the University of Limerick?
Well, it's a very long story, but I'm a mechanical engineer by training. I'm a bachelor's in mechanical engineering. Later on, I was working in manufacturing industry for a year. I was working in foundry and machine shop. Then after that, I changed that job to teaching academia. I was teaching subject of mechanical engineering. After that, I switched that and I opted for my master's. And it is in master's that I actually found a project to be done in one of the research laboratories in India, which is a government laboratory. It is National Chemical Laboratory in Pune. So I was working with Dr. Amol Kulkarni. He is one of the pioneering scientists in chemical engineering and reactor design. So over there, I was doing my master's dissertation where I worked in micro reactors, micro channels. I was working in unifying the flows in parallel micro channels. It actually grew my interest to pursue my research in fluidic devices. So over there also, I was doing simulations and experimental validations of these devices. And then after my master's, I continued my research over there in CSIR, National Chemical Laboratory, Pune, where I worked with static mixers, impinging jet reactors, and impinging jet reactors for precipitation, anti-solvent precipitation, then static mixers for different applications, and even flow distribution. I was designing manifolds for unifying flow distribution in parallel channels. So after that, I was very much interested and clear to do my research in fluidic devices. And I was searching for positions. In the meantime, I joined industry as a CFD consultant at Tridimensional Solutions Pune, where I was doing just simulations, nothing else.
Okay,
just
but fluidic devices.
Yes.
All right. Okay.
I was doing industrial projects like tanks, plants, and everything. I mean, I was doing everything that could be simulated. I was simulating those things. That was my profile. So after that, then I got an opportunity to join my PhD at Barnall Institute at University of Limerick. My project is funded by Synthesis and Solid State Pharmaceutical Center, that is SSPC. It is a Science Foundation Ireland Research Center for Pharmaceuticals. So I'm doing my PhD under Professor Vivek Ranade. He's another one of the pioneering names in computational fluid dynamics and chemical engineering. So I work in multi-phase reactors and intensification group. So our entire group actually works. They work in multi-phase reactors, and of course, intensification. We try to intensify these processes by introducing different fluidic devices. So that's what we do, and that's the journey so far.
Okay, cool. So you worked basically in a similar field from your master's on. You already have some industry experience, so not just academic experience. How's that changed? Like, how's it to go, from university into industry, back to university? Is it very different, working cultures, or is it the same?
It is definitely different. And in university, you have the working style, and in the universities and academies are different. So you actually have very new things to do. Well, in industry, sometimes I personally, my personal experience is that industrial job gets a little bit monotonous. I'm not saying that it is wrong, but yeah, sometimes it actually happens. Yeah, it's a little bit monotonous, but I think research is more lively. So yes,
okay.
that's how it is.
Then I hope that you can continue to have such an interesting job. How long have you been doing your PhD now?
I'm in final year. I'm about to submit now. So
yeah. Okay. I'm not going to ask any more questions. When you're finished, nothing about your writing. We are not going to talk about this. It's okay. But good luck.
Yeah, thank you.
We already had a lot about different fluidic devices. What I learned have worked in different places, different countries, even on this. So on this podcast, we have a section which we call In Other Words. And for this, I would like you to pick just one research project and explain it to us in simple words, please.
Yeah, so the whole idea of using and optimizing fluidic devices to cater to specific process requirement is a little bit intriguing. I mean, I was a little bit interested in that. So what we did basically, and what we recently published a paper in Chemical Engineering Journal last year, and we were able to show that using these devices to augment stir tank reactor, standard stir tank reactor, to have direct control over particle size distribution of forming crystals. That is one of the good examples of usage of fluidic devices. So that is one of the research that I'm, very much. I'm very much proud to say. I mean, I would use the word proud that this was the first time that anybody had augmented stir tank reactor. So what we did basically was, we used the same model system of anti-solvent crystallization, methanol paracetamol. And initially what we did was we used a stir tank reactor, a standard stir tank reactor, which hosted a saturated solution of methanol paracetamol, and we added water as an anti-solvent. So then after the process was completed, we measured the particle size distribution. We had the saturated solution inside the stir tank reactor, and we pumped it out from the stir tank reactor and put it back inside the stir tank reactor. So this was a closed loop. So you pump out the solution from the stir tank reactor, you pump it in again. And now here what we did was we added anti-solvent inside that loop, outside the stir tank reactor. Now we had a significant reduction in particle size distribution.
Okay.
So just because we are adding the anti-solvent outside the stir tank reactor inside a T-junction, mixing little bit enhances, and because of this enhancement in mixing, you have reduction in particle size distribution, and the spread of the particle size distribution goes down. So now over here we use a simple T-junction. Now instead of T-junction, we used oscillator and diode, the vortex diode and oscillator we used. So with oscillator, the particle size came down again, and with vortex diode, it came down again. Now, one interesting thing that I forgot to mention is that that the vortex diode can create shock waves because of cavitation, the bubble, because of the bubble collapse. Now, most of the pharma industries, they use to control the particle size distribution. What they do is that they use a wet mill or a dry mill, a milling machine, basically just a mill, right? What they do is that they inject a solution of, let's say, with particles inside and a solution, they inject into the wet mill, and then they mill that crystals. They mill it literally. They break those crystals.
Okay, yeah.
Use the particle size. So now one interesting application of vortex diode is because it generates shock wave. Is actually these shock waves can break crystals. They literally break crystals.
So instead of the physical milling, you can use a shock wave.
Yes.
Formed in your liquids.
So we use that. So because we used the vortex diode in that study, there was significant reduction. I mean, it was visible reduction in particle size distribution. So that we were able to publish in Chemical Engineering Journal recently. And yeah, I mean, that is one of the research that that actually cemented that these fluidic devices work.
Okay, I think you're very right to be proud of this. Just because I think we haven't talked about this now, can you just give me a brief order of magnitude if we talk about particle sizes or particle size distributions, but what is the size roughly we're talking about?
With stir tank reactor, we had particle size, our average mean size of particles basically was something around 150, 140 microns. And then with just simple addition of T-junction, that particle size reduced by 20 microns. With fluidic introduction of fluidic oscillator, it reduced further by 20 microns. And then with our vortex diode, it's further reduced by 20 microns. So we reduced from particle size from 150 microns to, let's say, 100 microns. Which is not significantly more, not significant reduction. So what happens is that this research has been published long back in 90s, I think, 90s or 80s, that where you add your anti-solvent or where you add your second component inside the stir tank reactor actually has different mixing. So if you add it near impeller, you add it over the surface of the water, or you add somewhere inside the stir tank reactor, it changes. You cannot have a repeatable process in stir tank reactor. It's not that I'm not saying that it is not highly repeatable, but it is not repeatable, it is not highly repeatable. So there are a lot of error bars, and the spread of the particle size distribution is too long. Too broad. But usage of fluidic devices, because fluid mechanics never changes, because it's a virtue of geometry, and the geometry never changes.
Yeah.
So if you repeat the process, the error bars are too small. And even because the mixing is good, the spread of the distribution also reduces.
Okay, so it's not just mean value reduction, but also the spread.
Also the spread, yes.
And reproducibility. Okay, yes. Very cool. I think we all figured by now that you really like fluid with devices and the research you're doing on them, and it sounds really cool. But there are other aspects of being a scientist than just like, doing your simulations and doing the experiments. So what other aspects do you like about being a scientist, being a PhD student?
Well, certainly, being a scientist, I would say, is incredibly fulfilling. It is incredibly fulfilling for several reasons. Now, first and foremost is that this endless curiosity. You have this endless curiosity of finding out new things, and this endless curiosity is somehow is acting as is a driving force to carry forward research, and of course the pursuit of knowledge. So every day there is a new phenomena that takes place, and as it's after 200 years there is no solution for exact solution for Navier-Stokes equation. So you always have this. I'm not saying that I'm going to, because that's not my area, but still, there are a lot many beautiful concepts and aspects of being a scientist, that you always find new phenomena, you always find new concepts which are very much interesting, and it acts as a driving force. And then every day there is a chance to explore something new. So when I was working previously in fluidic devices, I never knew that there was an effect called as Quanda effect, that the jet sticks. So harnessing that for a device and using it for processing application was definitely something new that I tried to explore, right? And then, of course, there is challenging the existing idea is one of the aspects of being a scientist. So I'm not saying the stir tank reactor is a bad reactor, but I would say that using fluidic devices with non-moving parts actually has better advantage over stir tank reactors in certain cases, surely, if not all. And then the one thing that personally I feel being a scientist actually overhauls your look overall perspective towards life. So the ability of how you pursue your things in real life is slightly enhanced due to just as an occupational benefit, if not hazard, I would say. So yeah, that is the one of the things of being a researcher. Additionally, unraveling mysteries, conducting experiments, finding solution to real life problems brings to a certain sense, brings a sense of, let's say, accomplishment in one's life. And also, on personal life front, definitely science actually makes a good impact on personal life too, and subsequently on a larger spectra, to people and planet. So that's how it is. I mean, so whether it is through enhancing perception, developing new technologies, improving healthcare, or addressing environmental challenges, these are all the aspects that I am not working on everything of this, but we as a whole, as a scientific community, we are contributing a certain way for the betterment of society, and that's, I think, is the best part of being a scientist.
That is very true, and I don't think I can add anything to this. You said this very nicely, especially also the point what you said resonated with me, that you continue learning, and there's so much still to discover. It's not like we figured it all out. That's definitely not true, and it's very, very cool to stay curious and play. And
hashtag stay curious.
Okay. This sounds all very good, and like you really, enjoy being a scientist and enjoy your research. But, if nothing's perfect, so if you had 3 wishes to improve your research experience, what would they be?
One foremost thing that I have experienced now, I've been in doing my research since, like, let's say 2015. It's been over like 8 years now. One thing that I definitely want this to, and I think this is true across every fields, bridging mechanism between interdisciplinary fields. There has to be a bridge, so that there has to be certain mechanism that we are bridging interdisciplinary fields. So, for example, if I talk about fluid mechanics to a chemist, he will not understand anything. So there are certain things. I'm not saying that everybody doesn't know that, but if your reaction, let's assume that if your reaction time is very less, and your reactor's mixing time is more than that, it is not going to, I mean, that reactor has no that reactor has no role to play over there. So that's, also bridging these gaps of interdisciplinary fields, maybe, we might to some extent enhance the impact of our research. So bridging is essential. So if somebody is developing a process, we try to study that process, and then we try to make it continuous. But people are still stuck in let's say the conventional process, and they don't want to change.
Okay.
The resistance to change.
So chemists who are listening to this,
I'm sure they're going
please
to
go
hate me.
back to the beginning of the podcast. I can't explain. No, joke aside. I agree very much. Like, I think there, you speak your own language in every subfield, and you have your own bunch of literature, and it's sometimes, even among fields that are in principle neighboring, not always so easy to talk to each other and to get the others to read the relevant literature and so on.
So one example that I would like to give is that, in mechanical engineering, there is a device called as heat exchangers, a normal shell and tube type heat exchanger. Now, if we can use that shell and tube type heat exchanger as a reactor too, but the velocities in all the tubes are constant. We maintain, mechanical engineers know the calculations to maintain the velocities in the tubes constant. But when it comes to application for this chemical engineering, you want residence time distribution to be constant. I mean, inside all the tubes. So this, if we combine these things, we can use a shell and tube type heat exchanger as a reactor too. So that is one example that I would like to quote to interdisciplinary fields.
Okay, so that was your first wish. What's your second one?
Second is, this is the dream come true, basically. I work in simulations. Give me a supercomputer. Personal super.
Okay. I'm sorry. I should have said this in the beginning, but we actually cannot make your wishes come true. We just ask for them. I cannot give you a supercomputer. I'm very sorry.
No, that's fine. So basically, unlimited access to cutting edge technology. So of course, unrestricted use to. Why am I saying this of this computers things? Is because sometimes, what happens is that there is one cluster where everybody is using, and sometimes the job goes in queue, and there's a lot of time delays here and there. So I think unrestricted use for computational and experimental tools is second wish. Definitely, I would like to have that access to all the tools and
yeah. Very understandable. And your third wish?
I'm sure you're going to agree with the third wish. Sustainable for research funding and recognition.
Yeah, I think, like, we've asked this question a lot of people, and a lot of people say they want more money, like not for themselves, but for their research.
The research, yes. Last but not least, of course, money matters. Yeah. So yes, money, and then recognition is another thing that actually I would like to emphasize, and I love the work that Science Talk is doing in this field, and I truly appreciate you guys, because
thank you.
That is not something that people do to give recognition to at least researchers, because unsung heroes basically.
We try our best. Thank you. Okay, so your three wishes were more interdisciplinary or better interdisciplinary work, supercomputer, and more stable research funding. Basically, all three very valid. I really hope they come true for you. Or, I mean, the first one maybe comes true for all of us or for the whole research community. I think that's a very good point that becomes more and more important, and I hope we, manage to get there. Apart from this podcast, you will also have 1 week access to the Real Scientist Nano Twitter account. I'm still saying Twitter. That's everyone knows what I mean, right? So during this week, what can the followers expect?
So what I'm planning to do for this curation week, I mean, when I will be handling the Twitter account or the X account. So first, we'll introduce our group of multiphase reactors and intensification, our philosophy, and what are the areas which we are working in. And of course, then I'll write all the devices that we are working on. And then, of course, there will be some interesting applications that will be disclosed. So how can you use these devices for different applications? So we are working on, let's say, we are working on milk production, milk waste valorization of the dairy industries. We are working on personalized emulsions, and then we are working on crystallization too. And so these are broad spectrum of applications that we do in our group. And yes, what we do is that, I will try to first introduce the group and then eventually disclose few interesting things that we are doing as a group. And also, if I'm not sure, but I will also write something interesting in fluid mechanics. That is my plan for the week.
Sounds very good. And I think what I figured now is that these processes are important for so many different applications and processes that I didn't even know, you would use fluidic devices for.
Yeah.
So very much looking forward to this. Thank you so much for speaking with me, and looking forward to your week on the Twitter account as well. Yes.
Thank you very much. It's a pleasure. I cannot thank you more. Thank you very much for this opportunity again.
Thank you, and thanks all for listening or watching. Goodbye.
Thank you for listening to yet another episode of Under the Microscope. If you like this particular episode that you just listened to, feel free to check out our other more than 200 episodes with amazing scientists from all around the world, materials and nanoscientists, and do let us know what kind of science, what kind of material science you would like to hear more about, and we will try to get you a guest accordingly. Thank you for listening yet again. Really appreciate your support. And hey, do consider joining our mailing list. The details are in the episode description. Thank you. See you in the next episode. Bye.